All right, my name is Samuel Iser. We're going to be going over the preference on command that we had for our senior design project. We'll learn more about the system presentation. Just some background, I've been going to the racetrack a long time. My dad got me started doing that when I was 10. That's my 28 that I've built over many years. My first car had it almost 10 years now, since I was 14. I instruct with the local PCA club at HPEs, and there I am in a student's car. So what can you adjust with the damper? This is one of the most crucial things that we have in motorsports. There's compression and rebound. So if you look at that little red Miata, it's compressed when it's turned. That's the compression adjustment, and the other side is the extension. So you can use these to tune the car. We don't have enough time to go over into all that right now, but that's what you can tune in a damper. Usually these adjustments are manual, and because they're manual, you have to get out the car, waste track time on it, and it's pretty annoying. So there's a couple market options that allow you to do this remotely from in the cabin. So first, you have factory installed cars that have this. BMW has their EDC system, which is like electronic damper control. Cusco has their Econ system, and then Tyne has their EFC system. These are only these can only be installed on their damper systems. So Cusco only works on the Cusco product, Tyne only works on Tyne, and of course BMW and all the OE manufacturers have custom dampers for these. So our project proposal was to create a POC system that could be universally installed on at least one type of damper application. So that could be BC coilover, Koni, etc. In this case, you'll see what we chose. And this will save track time and should save your tire life. So just an overall project timeline. Usually these things have table of contents. However, since we're going over our whole project, we figured it'd be better to have a timeline, and just so y'all can keep in mind where we are. So this is our installation of our adjustable dampers. We're going to be going over next, because currently my car had no adjustable dampers at all before we started this. So the dampers we chose were from Koni. So they're one of the biggest aftermarket shock manufacturers. They're heavily involved in professional and grassroots motorsports since the 1960s. They have a large selection of dampers, and most importantly, they are adjustable via this knob at the top. So this is a very standard system they have for most of their shocks. Obviously this can change for some, but for the most part, this is constant. So we chose the front Koni Universal Racing Strip, and for the rear I chose a shock for a Porsche 914. So registering the front shocks, we have our strut spacer. So Koni says to install this if the shock does not match your tube length, which it did not, so we built a spacer for this. My dad actually machined this before he moved. So this is the strut spacer, and as you can see what it does in the housing in this illustration here. There's the machine product, and there's a strut assembly. As far as the rear, this is a bit more involved because it's a load-bearing sleeve. This goes in the rear trailing arm, as you can see here, and supports the entire weight of the car. We had to copy it from the original Bilstein shock that I had prior. And once we did that, we were able to do an FEA on it as well to verify, and it has a factor of safety of 1.5. We have hand calculations that back this up, and here's our FEA, or shear and cutting stress. We have no concern about the life of this part. Here's the car on track, happy with the dampers, the range of adjustments. And so that's done. We have adjustable dampers in the car. So how do they get adjusted? Like we said, they have a top thing for the adjuster that you can turn. It comes with this knob here that you basically are supposed to have with you, so I can leave it at home. I can forget I could lose it. And every time I got to get out of the car, I have to stop the car, I usually can't go into the hot pit, so I got to go to the pit end. So that's a waste of 2 laps in like a 20-minute session. And each lap is probably 2 minutes. That's a good bit of track time. And you can see the rear, it was actually pretty hard to adjust. I can still get in there, but it's quite a pain. As far as our EDC hardware, so that's our next step, right? So we're going to have some type of microcontroller to control this. We need something that's well documented. We need something that's compatible, so if we need drivers or anything for it, that can interface with it. So the Arduino was the obvious choice for prototyping. We need a user interface that they can interact with and tune the car. It's got to have wiring to connect all this, and then we need an actuator. So the actuator could be a servo or a stepper, and currently we don't know what size it needs to be or the stall torque. So this is breakaway torque. It should be stall torque, but for the purpose of we use this torque wrench. So this is a live torque wrench that when you torque, it'll show you the gauge input and how much force it takes. So we measured 2 Newton meters to move it, and once we had that, we knew how strong the stall torque of the motor had to be. As far as space constraints, it's kind of hard to measure something if you can't see it, right? So when you shut the hood, you can't see where the hood is. If the engine was out of the car, sure you can do it. Laser scanning also won't work because you won't get the top of the hood. So something that came to mind is whenever they build engines, they use modeling clay to determine piston to valve clearance. So we did something similar. We got some modeling clay, and then we built it around the adjuster, shut the hood, and that gave us our overall space constraint. And you're able to cut it away and measure the cross section to get the height. It's fairly tight at 1.75 inches between the top of the adjuster and the hood. But now we have our size. So from that, we're able to pick our servo motor. The servo motor had the torque requirement that we needed to overcome it. It was actually a bit stronger, so it was 2.5 newton meters, and our torque required was 2 newton meters. So design concepts. So there are a couple options. Ideally, you put it directly on top of the adjuster, but we just don't have enough space. You have the gear design, so you can move it off to the side, lower the stack height, and then you have the drive cable. So it's just a flexible cable that can transmit torsional motion. They have it usually for manually adjusting coilovers if they're behind panels. I've also seen it like in flexible screwdrivers and stuff, so that was our other method. So from that, we put a design matrix together to weigh which was the best option. So as you can see, durability was really important to us, cost was important to us, easy to construct, not as much, adaptability, pretty important. And then we have compactness. Basically, the cable method won, so that's what we picked. From there, we designed it in SolidWorks, and then we prototyped and 3D printed something. From there, that's all wrong. It did not seem durable enough, so we were losing a bunch of accuracy whenever it would twist, and I just didn't trust the cable in long-term use, especially at that severe an angle. So due to that, we had to do a redesign, and we went to gear design, and we wanted to keep it consistent for the front and the rear. So the redesign was a pretty crucial moment for us, but it just seemed like the stronger, more robust option. As you can see, it meets the hood requirements. The base plate is securely mounted, and then we can change the breakaway torque for the gears, and there's just some tunability with this design. So there we go. We have our design. We have dampers in the car that we can adjust. So now we have to manufacture this. And just to go over the rear, we just can't make this work with the gear design. There's just not enough space. Originally, I was going to drill this hole for a cable, and then you can remote mount the servo with the cable design, but we just scratched it, and then we're only going to focus on the front for a proof of concept. So as far as procurement, we obviously don't want to build everything from scratch, so these are what we were able to source. We were able to get the standoff, the servo bracket, obviously the servo motor, gears, bearings, electronics from other places, and then we were able to get some raw materials for prototyping from the scrap box. Prototyping. So the parts we need to prototype to make sure they fit was going to be the base plate, the bearing block, and the adjuster tab, the gear shaft adapter. We were prototyped these 3D printed parts, and everything looked well. We got good alignment of the bolt holes, the gear engagement, and it's fairly serviceable. Since it was all plastic, the biggest problem so far was deflection, and nothing was threaded. So it wasn't that permanent, of course, so we wanted to move to metal. So we machined everything out of metal. We made...
What you said here is like some processes, and these processes led to the issues, and that's our final thing.
Okay. So as far as machining, these are the process that led us to our final prototype here. We did face milling, slot milling, bandsaw, base plate, bearing block. At this point, my father had moved, so Arthur really saved our butt here, and then Carlos with the water jet cut. I mean, we wouldn't be able to do it without them, so I just want to give this moment to thank them. And as far as programming, basically, I usually turn the knob, and then it'll turn the servo motor. We have a button saved for a home position in case something gets messed up, we just want to quickly go back to the middle. Testing with the metal prototype. So at this point, before it was moving fairly sluggish, and we assumed it was because it was deflecting so much. Once we went to the metal, that did go away. Everything was securely mounted, it was turning, but it was still fairly sluggish, and the weirdest thing was the screen was flickering, and we couldn't figure out why that was. It was because we were basically maxing out the voltage. So we were operating the servo at 5 volts, because that's what the Arduino puts out, and it needed to be operated at 7.4 volts. So
8.4. Oh, for the other one.
what are we at on time?
9 minutes and 42 seconds.
Okay, so from there we were able to troubleshoot what was going on, and we realized that 1, we were underpowering the motor this whole time. 2, was that the screen flashing is obviously really bad for the system, so we needed some type of separate voltage source for just the stepper motor. So that's where we were able to get this voltage step down converter. So the car is 12 volts, we're able to step it down to the 7 or 8 a servo motor would normally require. So that was a simple fix. And then from there, we powered the servo with the correct voltage to get the 2.5 green meters, and it was still not as snappy as we wanted. And so from there, we actually had to up to another motor, and we did lose some degrees of turn with this, but it was we deemed it like not worrying about it. So the results, we got a new servo motor, and then we got the new step down converter. The wiring harness. So this was actually I've wired stuff before, I've repaired wiring. It's actually really difficult because I have something in the car I need to power. I have a controller in the car, there's just a firewall, so I wanted to minimize wiring. So one of my friends parts out cars, I was able to get a bunch of wire from him. I had a recyclable wiring harness, just with a bunch of different color wires. As you can see, the LCD has 4 wires, that's in the car. The organ car, there's 5 wires. The button, that's also in the car, that's 5 wires. The voltage step down though is 4 wires, and it needs a power wire from the engine bay. The servos need all 6 wires in total going to the engine bay. But luckily we got it all sorted out. I was very happy with the end product in the engine bay. It had no sheathing, it's very permanent, minimal clutter. I mean, it's a little more clutter than the rest of the engine bay. So, as far as the interior product, it's easily reachable for the driver. The display is easy to read, and it's fairly serviceable. Something to note here, since we're using an Arduino, the pinouts for it, they don't have a very good connection. So if we're doing some, well, we'll get to what we'll do in the future. But as far as install, you can see we have exploded components of all the parts. Here's it fully assembled, and then that's on both sides without the covers on. All parts are designed and machined to have a snug and easy fit. They did. They'd only need 3 Allen wrenches to assemble everything, and you can pre-assemble most of it before you put on the car. It's pretty easy to maintain, easy to access everything, and most importantly, the parts are interchangeable. And then here's an example of our final product. How do you? Well, that might be.
Figure that out.
Somebody stand there just baseball. Oh, with the mouse. Somebody's gotta sit there.
So as you can see, just a quick test run we had in the parking lot. You can see as we adjust from the car, the knob is turning, so we're adjusting the shock. We're going to capture this on the GoPro, so the parking lot real quick. I wasn't too interested in the suction mounts, but we on the street with it.
We're gonna have to turn it to
Yeah.
the ball.
So just to conclude, so now we no longer have to get out the car and manually adjust everything. We have a fully contained system with a controller, machine parts, servo, it's all ready to go. We can do rebound adjustment from inside the car. This shock doesn't have a compression adjustment, so that needs to be fixed. We got increasing tire life. So basically, I think maybe if we have enough time, I think we could do an inclusion part 2 on the benefits. Thoughts? We're gonna run it through this fast because we're at 13 minutes, so it'd be like another minute to go over it. So I'm gonna make that slide. No? Okay, we're at 13 minutes, right? So here we just have, I feel like I can make a slide to kind of expand on this. It's pretty hard. Someone's gonna have to memorize this. They're gonna have to memorize like what a heat cycle is for a tire.
That's me, I got it.
Okay.
Just break it down and I'll remember.
Okay, it's on the poster for that, and then the increase in track time, but it should all be on the poster. But, so I can go over that with you visually, and then our skill sets gained for the project. We don't want that bullet pointed. I mean, so skill sets.
No, I highlighted it too, so we can.
Okay, so that's why I think maybe conclusion continued.
Okay.
So,
Alright, go next.
so Gantt chart for scheduling, 100%. Let's go. This was the final cost for our product.
For the set in the front.
For a set in the front, so we met our original requirement of $460, which you didn't say anywhere in the PowerPoint before, but that's fine. And that's,
Yeah.
that's
Alright,
my-
you can hit
I wasn't too happy with that, that's fine.
the